common part symbol, private part symbol 1 and private part symbol 2. Okay, so this is combined, that is superimposed. These three things, that is S1, S2 and SC, all these three things are superimposed and a transmit signal is formed. Okay, so this transmit signal is then transmitted through the channel, and this equation is, you can convert this equation into any form. Okay, this is a RSMA transmit signal equation. This transmit signal equation can be converted either to NOMA or to SDMA also, or to OMA also. Okay, so that is given by this table. So before that, let me show you an example. Here, 4-bit user message is taken, and this user message, first bit A1, second bit is given as A2, third bit is given as A3, and fourth bit is given as A4. And these bits are actually splitted. So that is message splitting. The first 2 bits are given to, that is A1 and A2 are given to the common part. Okay, and the remaining A3 and A4 are considered as the private part. So if I am having 0, 0, 1, 0, 0, 0 is given to the common part, and 1, 0 is taken as a private part. Okay, so common part is taken and private part is also found. Similarly, a 3-bit user message for other user. Okay, that is for the user 2. That's why it is given as user 2 here. So the first bit is actually given as a common part message. It is contributed towards the common part. The remaining B2 and B3 is considered as a private part. Okay, in this way the common message is formed. Okay, so having said that, now let's get into the subsets of RSMA. As I said, the RSMA equation that is given here, we can manipulate this PC, P1 and P2. This PC, P1 and P2 are the precoder vectors. Okay, this PC, P1 and P2 will be inside this linear precoder, and this PC, P1 and P2 corresponds to, is based on the channel state information. Okay, channel state information between the transmitter and user 1 and transmitter and user 2. Okay, now based on this values of P1, P2 and P3, we can design SDMA, NOMA, OMA, multicasting, and rate splitting from this one equation itself. Okay, if we directly make this S1, if you are directly connecting to W1, and this W2 line, if you are directly considering it as S2, then we can make this RSMA equation as a SDMA equation. Okay, that means PC is equal to 0. Okay, in NOMA, if you are putting this user 2 message in common part and user 1 message as such, there is no splitting, nothing, rate splitting, nothing is happening there. That means P2 you make it as 0, then you can experience a NOMA there. I mean, you can convert this RSMA equation to a NOMA one. And the OMA, orthogonal multiple access, in that at one part of time you need to send one user's message, and the second part of time you need to send another user's message. So this S1 is sent at the first part of the message. Okay, so remaining 2 parts are deactivated. That is P2 and S2 are P2 and the common part are made to 0. There is nothing being sent there. Okay, so that corresponds to OMA. And multicasting means we will be sending this W1 and W2 together. Okay, that concept we are not looking into so strong. So let's go into rate splitting. In rate splitting, as I was telling earlier, the common part message is formed from both the user's message, and the remaining part of the message will be considered as private part of user 1 message and private part of user 2 message. Okay, so this is about RSMA and why we are moving from NOVA to RSMA, particularly when it comes to multi-antenna scenario. Okay, NOMA completely fails at multi-antenna scenario, so we have no other choice except to move towards RSMA. It's a most efficient type of multiple access scheme as of now. So many other schemes will be may be developed on this RSMA, but without NOMA we cannot understand RSMA also. So we need, for a comparison, we are supposed to discuss about NOMA and its merits also, and its demerits also. Okay, so this is the overall sum rate comparison of multi-user linear precoding. That is the SDMA that we have derived, and RSMA. This is the comparison. We can see that the blue line corresponds to zero forcing, and the red line corresponds to rate splitting zero forcing. and the plot is between the rate and the SNR, and this k is equal to the k is number of users, m is the number of antennas. So when my number of antennas is 2, I have a performance given. But when my k is equal to m is equal to 4, that is the number of users and the number of antennas is equal to 4, then I have a better rate performance. But when you compare between the normal zero forcing and the rate splitting zero forcing, that is SDMA and the RSMA scheme, when we compare, this RSMA scheme has a better rate when compared to SDMA. Okay, so this is the advantage of going for rate splitting multiple access scheme. And with respect to the antenna also, number of antennas also, it is getting increased. Why they have differentiated with respect to antenna is that because as we keep increasing the number of antennas, proportionately my performance will also be getting better and better. Okay, that's what they are trying to say, because increasing the antenna is increasing the complexity. So we are supposed to know what happened. What is that? Is there a merit in increasing the number of antennas? Is it worth it to have more number of antennas for transmission? So yes, when you are using RSMA or SDMA, it is definitely worth it. But with respect to NOMA, it is not. Okay. So this is about the applications of RSMA. So the part of RSMA is done. I was planning to give another one also. Just a minute. There is OTFS. So before entering into OTFS, is there any doubts for anyone to in RSMA? I'm happy to answer.
Participants, you have any doubts, you can ask. Sir, I think they don't have any doubts.
We can proceed.
Last we can take, sir. And
okay.
Once again.
Okay, Dr. Sri.
Yeah.
And yeah, so this is another exciting technology that is coming up in 6G. So when I was doing my PhD, OFDM was considered as a better technology with respect to dealing with the frequency selective fading channel, and that forms a part of 4G also. Here OTFS, that is orthogonal time frequency space modulation. Okay, so orthogonal time frequency space modulation. So is this orthogonal with respect to time? Is the signal will be orthogonal with respect to time, with respect to frequency, and with respect to space? On all three aspects, uh, is it orthogonal? So that is what one has to check when it comes to OTFS to understand OTFS. Okay, so to discuss about OTFS, before that we need to understand what are the two concepts. One is Doppler spread and another one is a delay spread. The left side one deals explains about the delay spread, and the right part of the slide explains about the Doppler spread. Here you can see it is a simple simple transmission model. A base station is transmitting information to the user. Okay, to the user. One is a direct path, LOS path, and another one is a reflected path. Now, the direct path is traveling a distance of R1, which is the shortest path we have. Okay, so the direct path is traveling a distance of R1. So the delay of LOS path, the delay is actually corresponds to tau 1. That means what is the delay to reach here? That is given by tau 1 is equal to R1 divided by C. C corresponds to the speed of the light. Okay. Now, what about the delay that corresponds to the reflected path? Reflected path is traveling an additional distance. Okay. So reflected path travels an additional distance. So we have the distance more, that is R2 plus R3. is the distance we have for the reflected path. It is higher the distance, so the delay will be a little more higher. So you can we can say that I'll just draw this. I don't know. Wait, it is not working. Okay, the pen is not working here. Anyway, so we can say a pulse is there. A pulse with higher strength is there at a delay of tau 1. Tau 2 is even more larger delay. So tau 2 corresponds to a pulse that happens after tau 1, but the pulse strength will be lesser. Why? Because the signal is reflected from a building. So since the signal is reflected from a building, the signal strength will be very less when compared to the LOS path. So that's why we can say that is actually the delay profile. Okay. So the delay spread is actually given by what is the difference between the two paths. That is the two paths delay. Tau 2 minus tau 1. If you take the difference, that is the delay spread actually. Okay. So that is what is given here. And when we go to the Doppler spread is related with the relative motion between the transmitter and the receiver. Okay, so let's say I'm transmitting at a frequency of 2.4 gigahertz, and if a user is stationary, let's say you are sitting inside, you are sitting on a chair and you are not moving anywhere, or you are just walking, no issues. So you are not moving at a very high speed. Uh, at that time, if frequency is fixed and and the signal is getting transmitted, the frequency is fixed and will be received at the receiver also, no issues. But when the user is moving, why we let's say when you are going in a train, uh, our call quality is not so good. When you are moving in a fast bus or in a fast car, a fast moving car, we can see that the signal gets disconnected. That means the connection of the mobile gets disconnected very rapidly. This is because of the fact that uh, the orthogonality between the subcarriers will be not correct. I mean, will be missed. So there is also a change in the carrier frequency. This is due to the fact that there is a change in the carrier frequency that is called a Doppler frequency. So when a car is when a moving person is going towards a base station, so you can see that the Doppler frequency is calculated like this. Let's say the car is traveling in the road, that it is moving at a speed of v. You can say that the Doppler frequency is actually given by carrier frequency times the velocity divided by the velocity of the light. Okay, so that gives the Doppler frequency of the LOS path. Okay, and whereas the reflected path will have a Doppler frequency like this, where the reflected path makes an angle of theta with respect to my direction of the car. So based on this theta, we are adding a cos theta here, cos theta term here. So for that also there is a separate Doppler frequency is there. So the difference among these two frequencies is actually known as the Doppler frequency. Okay, so we need to know these two before we enter into the concept called orthogonal time frequency uh, multiplexing. Okay, okay. Now here you can see this is my conventional OFDM. Whatever is given here is the conventional OFDM. There you can see the subcarriers are tightly packed, and it is to be noted that when a subcarrier is having a peak, when a one subcarrier is having a peak, other subcarriers are having a zero value there. The frequency response, the gain is actually equal to zero. Okay. Similarly, you can see the green color subcarriers having a peak value. Remaining all the subcarrier values are equal to zero. So in that way, you have the multiple subcarriers here. And when we are when a person is moving from moving in a faster moving vehicle, then and he is trying to establish a connection, you can see the subcarriers is bringing in something called ICI, intercarrier interference. Why we call that as an intercarrier interference is that here, when there is a peak, other subcarrier values are zero. But due to the motion, relative motion, there is a Doppler frequency coming in. That Doppler frequency will actually get added to the actual carrier frequency. So because of that, you can see it experiences the null will not be happening at the peak of one subcarrier. Okay, so other subcarriers will have some values. So in that way, we get something called ICI, intercarrier interference. Okay, so OFDM is not practically a feasible solution for a high mobility scenarios. That means the channel is keep varying. It is very dynamically varying, and we cannot keep estimating the channel at each and every time instant at a very short time instances. Okay, so that's why we are moving for a technology called OTFS. So of course, we are very much aware of the uh, pros and cons of OFDM. The some of the cons of OFDM are it is difficult to equalize the signal with the Doppler effect. Okay, and we have mm, and we can say that the channel estimation and equalization is very difficult for the highly varying channels. Okay, highly time varying channels. So OTFS is used to mitigate this issue. So OTFS converts into a different domain, converts the conventional signal into a different domain, and it makes sure it is handling the uh, high mobility scenario very well. Okay, so here in this OTFS, there is a domain called like time frequency domain. Uh, a domain called delayed Doppler domain is there. Okay, delayed Doppler domain is there. So this delayed Doppler domain is used to define this OTFS. That means in one axis we have delay, and in another axis we have a Doppler there. Okay, so let's say I'll use take my complete screen. Okay, okay. So here I will use for OTFS. Okay, basically we are converting into a two-dimensional part, that is delay Doppler, delay Doppler domain, that is DD domain. Okay, basically we have a time frequency domain also. Okay, that we already know. So basically we convert uh, a message, a vector of message into a matrix. Okay, that matrix is subjected to is being sent through the channel with multiple taps. Okay, and that channel is actually given by, let's say I have a channel like this. Okay, so that is H n comma m. Okay, so this one corresponds to, let me just take this one more axis. This axis corresponds to frequency, and this axis corresponds to time. Okay, so with respect to frequency and with respect to time also, my channel response is varying very rapidly. Let's say I have a response like this. Okay, for the first time instant, and for the next time instant, let me say, and for the next time instant, let me just say that it is randomly having some frequency responses like this. Okay, for every time instant, it is having a responses like this. Okay, so you can see here it could be even more accurate. Okay, so in this way my channel is there. That means with respect to time and with respect to frequency, my channel is keep varying, the channel gain is keep varying. Okay, so this is my TF domain. Okay, now we are converting this to delay Doppler domain. So in delay Doppler domain we have three axes similarly, so that I am representing with h of k comma l. Okay, k corresponds to delay and l corresponds to Doppler. Okay, so this is Doppler, this is delay, right? And we have the corresponding h of k comma l matrix. Okay, this is the delay Doppler domain. And here if I check the same response, whatever we read, this is a very not so good looking response we have here. We have a very random response which is very hard to estimate time to time. So we are going for a delayed Doppler domain. In the delayed Doppler domain, if you see, there will be two impulses only. Okay, now the idea of going into delayed Doppler domain is that when when a channel is continuously varying, that means when a vehicle is moving very fast, having in contact with the base station, this channel every time it has to be keep estimating, because surrounding the channel we have multiple objects. So this, instead of estimating the channel completely, we can estimate what is the delay and what is the Doppler. Okay, if we could able to keep estimating this delay and Doppler, it would be much easier to handle this kind of fast varying channel scenario. Okay, so that's why we go for a delay Doppler domain, and this is basically done by a process called ISFFT. Okay, inverse symplectic fast Fourier transform. Okay, here the input is a delay Doppler domain input, and the output is time frequency domain. Okay, this is time frequency. N comma m corresponds to time frequency, and k comma l corresponds to, this is time frequency. And once this is converted to time frequency domain, it is subjected to Heisenberg transform, which converts the time frequency to time domain. Okay, so in this way we convert from one domain, that is the time frequency domain, to the delay Doppler domain. Okay, so having this in mind, okay, we have, so just in case if I want to convert this time frequency domain to again back to delay Doppler domain, then I want to do the SF50. That's not ISFP, the symplectic fast Fourier transform we can do, and we can convert that to a delay Doppler domain. So this ISF50 basically what it means is that I want to take it is literally like multiplying my signal with two DFT matrices. Okay, so let's say I have x of k comma l, that is multiplied by two DFT matrices, DFT1 matrix, and another one is DFT2 matrix. Okay, where the DFT1 matrix size need not to be equal to DFT2 matrix size. Okay, this could be 16, this could be 8, this could be any other value, 64, this could be 32. Like that, any combination you can take. So on doing this, so we can get what is my time domain response, h of n comma n. Okay, so first we need to simplify the problem. So we are going for the delay Doppler domain, or the delay Doppler domain. Then only we can able to realize this OTFS. Okay, now getting back to the OTFS. Yeah. So getting back to the OTFS, we can see, and this is the figure I wanted to show. Actually, this is a figure posted by so you can see this is the figure posted by OTFS, the person who is predominantly working in OTFS, his name is Hadani, Dr. Hadani. You can check his video. There are a lot of videos which explains this OTFS concepts, and this picture is taken from his website, and you can see there are there is a base station antenna here. There is a base station antenna here, and there is a car and a user is here. Okay, this is a downlink scenario. Remember, the the base station is trying to communicate with this person who is sitting inside this particular car. Just a minute. I hope you can see my cursor, so not an issue. Now, this base station signal is coming directly to the user, but it will not just that, because it is the signal will be reflected from various other sources too, prominent sources too. Okay, so the signal is reflecting from one another car that is traveling towards the base station only, and it is traveling along with the actual user's car, and there is a truck that is traveling in the opposite direction. Remember, it is traveling in the exact opposite direction, and you can see the distance traveled by the red one. Okay, so there are various colors are used. Now we are going to plot this in a delay Doppler domain graph. Okay, that is given here. Okay, here you can see the delay is given by 0, 1, 2, 3, 4, and Doppler, it could be either positive or negative. Okay, because when a vehicle is moving towards a base station, you can add the Doppler frequency, and when the vehicle is moving away from the base station, you can subtract the frequency. Okay, now here the blue line, just take that is a straight line. Okay, of course there will be a Doppler, and that Doppler is positive, that the Doppler will get added to the center frequency, or carrier frequency, we can say carrier frequency. So that carrier frequency will that corresponding Doppler, and you can see the size of the blue color dot here that corresponds to this blue line. It is very high too. That means the intensity of the signal is very high there. That's what it means, literally means, and it has a Doppler of 1. Whereas a reflected path is traveling some more additional time. Okay, when compared to LOS path, the reflected path, the yellow color path is traveling more time. So I have added one delay there. Okay, there is one delay is happening there, and also remember, this fellow is also moving. This fellow is also moving. Okay, so the white car, the car that is reflecting is also moving. The car which has the user is also moving. So there will be obviously some more Doppler frequency will be there. So we are giving a Doppler of 2 for that, and the intensity is a little lesser because it is traveling a larger distance compared to the blue line. Similarly, the red line, you can see the red line is traveling a larger distance, and it is reaching here, and the Doppler is negative here. Remember, the Doppler is negative here because the reflecting object is traveling in the away direction. Okay, away from the base station, so the frequency will actually be subtracted. That's why there is a negative Doppler there, and the delay is also so high because it has to travel a long distance. Okay, let's say if this truck is very nearby and it is traveling in the opposite direction. Okay, so there you can see the delay will be very lesser. Okay, and this is how the Doppler and delay is represented, and yeah, so now let me just start with the coding part, because some kind of coding needs to be done. Uh, so and this code actually this code is actually from GitHub. Okay, this is a normal one, and I have I want to define a Doppler signal, that is x underscore dd. Okay, delay Doppler domain. In delay Doppler domain, I am defining a signal x underscore dd is zeros of m comma n, and that m and n are given by m is equal to 64 and n is equal to 32. Okay, and this is going to be converted into a time frequency axis. This is going to be converted into a time frequency axis thing. So this is in delay Doppler. Remember, in delay Doppler, I want to include two impulses. Okay, so two impulses I am including at random places. Let's say, okay, one is at 3,1. Randomly, I am inserting one impulse there, and another one is 3,2 actually. Okay, and another place is 2,2. Okay, and another place is 2,2. I'm inserting a pulse. Okay, so this is a impulse in. These are all the impulses in delayed Doppler domain. Let's see what happens in the time frequency domain. How to convert this to time frequency domain is that so my x is going to convert it to time frequency domain, and from the delayed Doppler domain. So my delayed Doppler domain signal, let me just give first. Delayed Doppler domain is getting converted to the time frequency domain. So for that, I need to multiply with the two matrices. Okay, this is the f of t matrix, fm and fn Hermitian. This hyphen refers to Hermitian. What is this fm and fn? Is that this fm f suffix m is actually equal to 1 divided by square root of capital M into DFT matrix. DFT MTX means DFT matrix. This is a MATLAB command. You can check in help. Okay, so that will be defined similarly. MATLAB for N is also defined. Now this is now converted into time frequency domain. Now this time frequency domain is going to be converted to a time domain. Okay, after doing Heisenberg transform, we can realize the time domain. But before that, let us plot uh, how this delayed Doppler domain looks like. Okay, so for that, I'm just putting figure. Okay. So bar 3, it's a three-dimensional bar diagram. X underscore dd, axis tight. Okay, and X label is Doppler, and my Y label is delay. My Y label is delay. Okay, this is the basis function that I have given for Doppler domain, delay Doppler domain. Let me just plot this first. I need to save it. Okay, here you can see this is the two impulses I have given there. Okay, uh, two impulses you can see there, and they are tightly packed, and the remaining everything are zero. Now we are going to convert this into a time frequency domain that has already been done. X of tf, x underscore tf corresponds to time frequency domain, and this time frequency domain we can still plot it like this corresponds to surf of Now, real part of. Let's see how this values looks like. Basically, you can see this is a 64 cross 64. I put a breakpoint and I'm showing you this. So this FM is a 64 cross 64 size, and this FN is a 32 cross 32 DFT matrix, and this FM matrix is multiplied FM and FN matrix are multiplied with the XDD to convert the delayed upload domain. This is what ISFFT is. ISFFT is. Okay. So now taking this into account, we are plotting the X in TF domain. Okay, so TF domain corresponds to time and subcarrier. Okay, this is time, this is subcarrier. Okay, so if we are plotting this, okay, so we have axis, axis. Okay, XTF is actually XTF has a problem because XTF is a complex number. Remember, because we are multiplying with the matrix DFT matrices, so it is a complex number. So we are not supposed to. Okay, so let me put real of XTF. Okay, so if we run this, we could able to see the real part, how the real part is getting plotted in subcarrier and time domain. That is the time frequency domain. And similarly, we can show how the imaginary part is also getting plotted there. Okay, how much it is varying, you can see there. Okay, this is the basic problem with respect to the time frequency domain. Okay, now let's enter into the time domain for this. Okay, this time domain we can convert. We can convert this to a time domain just by putting x underscore t is actually equal to fm into x underscore time frequency, Heisenberg transform. Okay, this corresponds to Heisenberg transform. And you can plot this in a similar way. Okay, plot this in a similar way. That means the plot. Remember, this is a time axis. Okay, so x-axis is time, and we put the axis tight, and we are going to plot with respect to time. So the time is for once we are converting this to x underscore t, that is time axis, we need to make it linear. Linear in the sense as a vector. Okay, right now this is as a matrix. We need to reshape it as a vector. So I am reshaping it as a vector, So reshape x underscore t or m into n comma 1. Okay, so this yes we are going to plot now, and this yes real part of yes we are going to plot now. So we have real part of yes we are going to plot. This is going to be plotted from 0 to of yes. Okay, this is going to be one axis, and this is actually given by this is actually scaled by one. Let's say 15 kilohertz. We are having a delta f value, so we have 1 divided by 15 kilohertz. So m is uh, 1 divided by 15 kilohertz, right? So m into 15 E3. Okay. So if we have this, will be okay. There is some kind of error that is happening there. Vectors must be of same length. Let me just check 2048. So this is length minus 1. So this is one length extra. So I have, okay, so this is my real part, and this is the time domain equivalent of my whatever time frequency signal we have seen here. Time frequency domain, from time frequency domain we are converting to time domain, which is given like this. Okay, so this is about the OTFS signal and delay Doppler domain. You could have got an idea of OTFS, how to proceed with OTFS actually. Of course, there are a lot of mathematics involved behind this. So we need to represent this delay and Doppler, everything in the math, everything with a variable, and that can be uh, easily viewed in MATLAB. Okay? But how to make it more complexity, how to make the complexity less is that we have to convert it to some other domain. We need to convert it back to, again to the time domain for transmission. Okay, so this is the idea of OTFS. Yeah. Now with that, I just conclude the session. If you have any doubts, you can please let me know. I'll wait for another 5 minutes.
Hello, sir.
Ah, yes.
Sir, I think audience one or two have the question, sir.
Yeah.
You can ask.
Good afternoon, sir.
Yeah, good afternoon.
Sir, my name is C.H. Babu, research scholar from JNT Kakinada, sir.
Hello, sir.
My question is how we can design OTFS system for UAV.
OTFS system for?
UAV, unmanned aerial vehicle.
Of course, many technologies are being combined with OTFS or RSMA, whatever it is. Many technologies are being combined. When it
Okay, sir.
comes to UAV,
Yes, sir.
UAV downlink, the channel will be quite different because base station height is lesser when compared to UAV. I mean, very lesser. So the way the delay Doppler is varying will be a little more lesser because when the amount of speed a vehicle is moving, when we look from the base station point of view, the speed a vehicle goes is very high, whereas when we look from the UAV point of view, the vehicle speed will seem to be very less. So from the UAV point of view, of course the channel and everything will be different, but the OTFS technique will remains the same. So OTFS technique will be the same, the ISFFT or the ZAC transform, whatever available in the literature, you can use it.
Okay, sir. Okay, sir. Thank you, sir. Thank you very much.
Thank you.
Sir, good evening, sir.
Good evening, sir.
My question is, how does RSMA improve energy efficiency in wireless networks?
How is RSMA is energy efficient in wireless networks? I hope that is your question. RSMA is
Yes, sir.
energy efficient. We can say RSMA is energy efficient. In one way, comparatively, we can say it is energy efficient because in NOMA, multiple layers of SIC has to be done. So if there are more number of users, multiple layers of SIC has to be done, and um, uh, every user are treated equally there. So overall, if you see, the energy efficiency will be better for RSMA when compared to, because the computational complexity involved in doing the SIC would be so greater for multi-layer NOMA, that is more number of users NOMA. Uh, But here only one layer of SIC is there. Every user does has that. So definitely RSMA has an edge in energy efficiency when compared to NOMA.
Thank you, sir.
Yeah. Thank you.
Sir, good evening, sir. I am Srinivas, sir. I don't have any questions, sir.
Okay.
Sir,
Okay. That
sir,
was
I am
fine.
very much thankful to Dr. M. Surendra, sir, for accepting our invitation within the short period. So the sir has explained the concept of NOMA, RSMA, OTFS very well, which is very useful for the participants. Sir, could you turn on video, sir? We will take the one group photo with you.
Okay. Can you give me a minute? Yeah.
Yes, sir. Yes, sir. Yes, sir.
Okay. Taken.
Sir, we will take group photos, sir. So you
Yeah.
will be
Yes. Yes.
virtually available and we are physically joining on the screen along with you, sir.
Yeah. Please.
The whole participants are joining near the screen and will take photo along with you.
Okay. Okay. Okay.
Chestan. Sir, could you please stop screen sharing, sir? Nice. అక్కడే కాదు అక్కడే. Clear, sir. Sir, everybody is joining there. Please wait, sir. చెప్పాను మేడం గారు రండి లేడీస్ సార్ కనపడాలి సార్ కనిపిస్తున్నారు
Sir, thank you, sir. Now you can switch off that video. Hello, sir. You are unmute.
Thank you all. Thank you, Dr. Srinivas, for the opportunity. Thank you.
Yes, sir. Thank you, sir.
Thank you.